Morning, everybody, and hello, YouTube. So just to get started with another fine day of the theory of the Galois. Awesome. So the reading for today is 16.8 and 16.9. I don't think we'll finish 16.9 today, 16.9 today. The quartics are pretty. There's a lot going on there, so then I probably will continue that. Finish that up on Wednesday. And then we'll start. Then we'll tackle. We're going to skip 1610, which is a wonderful section that we will skip, unless we have to go back to it. There's some possibility of that. Maybe we'll see. So actually, I have to say that as soon as we get into 16.9, we're now getting the part which I have never taught before in anything, and so there is definitely a possibility that I will have to backtrack and cut. Well, it'll be an adventure for all of us at the same time. Something like that. Anyway, okay, so let's see. So I guess prompts at 10 is due today, technically. Good morning, Robert. Right, so then we'll have a sort of take-home exam, which I guess I should write tomorrow. That would probably be a good idea. It'd just be sort of variations on homework problems that you have seen from problem sets. I think probably 7, 8, 9, and 10, something like that. Anyway, but we'll see what happens, and I'll give you more details of that on Wednesday. Let's see. All right, so we ready to go? Excellent. Approve. I like that Y factorial. Rockin'. Okay, let's do this. Okay, so this today I actually remember to put in my Galois theory in a nutshell slide. So let's take a look at that. So here is Galois theory in a nutshell again. So suppose K is the splitting field over F of some irreducible polynomial little f. So Galois theory relates the field theoretic properties of K as an extension of F and the group theoretic properties of the Galois group of K over F, the group of F automorphisms of K. And so, for example, G permutes the roots, which must be distinct. Oh, yeah, because we're in characteristic 0. Which is sort of our unstated assumption. But in characteristic 0, G permutes the roots, the distinct roots, alpha 1 through alpha n of F, as isomorphic to a transitive subgroup of Sm. So the main theorem of Galois theory says that there's a bijective inclusion reversing correspondence between the subgroups of G and the intermediate fields. Oh, I forgot to do that again. No, I'll put that in. So at some point I'll remember to do this, right? The intermediate fields. No, okay. Undo. All right, so yeah, this is going to drive me nuts. I just heard today that that Microsoft Word is officially making 2 spaces after a period an error, and I'm outraged by this. Though the rest of my family thinks I'm nuts. They all like 1 space. Anyway, sorry, what was I talking about? Okay, so yes, so the main theorem of Galois theory says there's a bijective correspondence between subgroups of the Galois group and intermediate fields between F and K that sends a subgroup to its fixed field, and the intermediate field to the Galois group of K over L. And remember, it's always a little tricky. It's the Galois group of the full extension over the intermediate field, and not sort of what's down here, which is sort of what you might think at first. The group of what's down here is obtained as follows. Or at least we have the following information. You can sort of actually do something similar to work out the group down here. Oh, my water boiler's ready. Anyway, so L as an extension of F is a Galois extension of F exactly when H is a normal, the corresponding subgroup H is a normal subgroup of G. It's nice to be able to lecture to musical accompaniment. In which case, the Galois group is of L as an extension of F, of L over F is G mod H. So as the quotient is that quotient group. All right, so that's what we've done up till last Wednesday. And now our immediate problem, a problem that we're looking at right now, which is the hard part, right? In terms of a course, at least, is to actually compute some stuff. So given a splitting field K of some polynomial f of x, compute the Galois group of K over F. Yeah, that's our sort of sole topic for today. Excuse me. And eventually, this is building toward in 1612. We're going to look at the question of when can alpha 1 through alpha n be written as a function of the coefficients of f expression using only case roots. So that is for which degree polynomials is there some generalization of the quadratic formula. And as we'll see, sort of maybe not directly. I mean, I guess you can Wikipedia it, but at least we'll see reference to the fact that there is such a thing as a cubic formula, and there is such a thing as a quartic formula. But as we'll see, it follows from Galois theory that there is no such thing as the quintic formula. And so when there is such a formula, we say that f is solvable by radicals, and we'll have a lovely and sort of the canonical lovely thing that you learned at the end of Galois theory is an expression, is a theorem relating a particular group theoretic structure of the Galois group, and whether the sort of corresponding equation is solvable by radicals. And you know, if you've seen Galois theory before, I'm almost certainly somebody's mentioned that to you because it's so awesome. But yeah, we'll look at that in some detail in this course as well. Okay. So, any questions so far, or are we good? Are we good so far? Yeah. So Ravi said, "How do you know which permutations are in the Galois group?" That's a very good question. And the answer is it's very difficult. Let's see, do we actually? Yes, so I think we will actually get to, I mean, there's no sort of like, oh my gosh, what would you actually do? Let me answer your question. And I'll stick a page in here. Okay. All right, so Ravi asked, question, how do you know, actually, oh no, I left this at too large a font, there we go. Question, how do you know, and actually let me sort of blow this up again. How do you know which permutations are in G? And so this is seemingly a straightforward question, right? The answer is it's really difficult. I don't want to make any blanket statements because I'm not an expert in Galois theory, but let me say I don't know of any, I don't personally know of any methods, any even brute force methods just say I don't personally know. Brute force methods for verifying if a particular permutation is in the Galois group of, say, K over F. But let me think about it. Let me get back to you on that. I bet it. So I bet if we Google brute force Galois group computation, there might be something out there. Well, but I'm not entirely sure. This may be a good question. So yeah. So right. So, but isn't this the same as finding G? However, we can use in practice in a course at least. Practice, if you don't have like a giant computer, if you're not using a computer to do this, you you narrow the suspects for G. And you find and use deduction to verify, to find certain elements of G, and thus eliminating enough suspects to figure out what G is. And I think the basic method that we'll see today by various okay, find things that are left unchanged by G. And Mon Apr, I see your question, by particular G. Comma, which will eliminate some suspects. I think that's really pretty much the method that we have. Right. So Mon Apr asks. So here's another question. And remember, C4 equals Z mod 4. So in homework, we usually know the order of G. For example, the order of G is 4. Yes, so often you can deduce that. Though that's actually not entirely easy to do either. So maybe the short answer is that none of this is super easy. And in fact, there are many interesting open problems. I cannot resist, and I should not, and I just add in another page here. Right, so how do we know the order of G? So for example, oops, let me move my face up there a little bit. Example, we know that if we know that the order of G is 4, but how do we know if it's C4 or Z2 cross Z2? So here's a partial answer. But we can deduce images. We can use some known elements, images of field elements, and the definition of automorphism to deduce the images of other elements. Okay, yeah, let me, so for example, remind me to do either square root of, there's two examples in the book, square root of 2 plus square root of 2, or square root, it's important that I get the number right. Square root of 4 plus square root of 7, okay. When we get to quartics. Right. So I think, yeah, Mon Apr, I think this does not really answer your question, but we will sort of get to an answer either by the end of the day, or I hope by the end of the day. So hopefully that'll, yeah, but oh, right, I was going to tell you an open problem. So So and this is a good well, I mean, this is an advanced sort of this is an expository thesis, but it's a very advanced expository thesis, and it sort of goes beyond my knowledge, but that's okay. That one of the things I like to do about in theses is to learn new stuff. So it's an open problem, meaning this is something. So this is a major open problem. The inverse Galois conjecture. Conjecture. Given in a finite G, there exists some extension Q, K of Q, such that, and there are variations of this, you can replace Q with something else, such that G of K over Q is G. So this has been open for quite some time. I don't know, probably as long as I think this is like an Emmy Noether thing. At least it sort of dates back to the era. So it's about 100 years old. So let me just guess, 100 years, open for 100 years, around 100 years. The inverse Galois conjecture. I'm sure somebody will Google this and look it up. But and correct me, but please do. Anyway, so the point is that it would be. The point is that here's a good master's thesis. Explain some work on the inverse Galois conjecture. I know like a little. I know enough about this. Inverse Galois conjecture. E.g., how the conjecture is not as hard. I can't remember. I think it just sort of fall. I think that's actually solved. If you get to replace Q with the thing that you want, then then there's actually a solution, and then there's actually a way to sort of and the sort of recent meaning the last 30 years, not that recent, but there over the last 30 years, a lot of work has been done, sort of trying to bootstrap this case to the full inverse Galois conjecture, the sort of inverse Galois conjecture over the rationals. Anyway, so so master's thesis explain how the conjecture can be solved. I can't remember this myself. In some cases, look, I'm like I feel brave about this. I'm exposing my ignorance on YouTube. There we go. In some cases, let me say at least in some cases, if K is a function field. I think that's right. So if you sort of get to, instead of starting off with the rationals and having to pick K, that one is unsolved. If you it's actually not so bad. I think either you pick or is it maybe it's K over C of T. I can't remember. I'll look it up for Wednesday. Okay, so yeah, so you guys have very good questions. Like, how did So we had two very good questions there. Let me pull back and look at them. One excellent question was how do we, if I have a particular permutation, how do I check if it's an automorph is in the Galois group? Well, that's not so easy. And in practice, that's not what I mean. I wonder, there must, I'm going to guess that there's some, maybe that I don't know a brute force method, but I can look it up. And I think there might exist brute force methods for determining whether a particular permutation is in the Galois group. So you can just beat it to death. That's always a good option with a problem. But in practice, you won't want to do that in a say homework problem. And So instead, you want to do something a little more subtle and eliminate certain cases by finding invariance. So and the second question was, how do we distinguish between these two things? Well, in general, actually, I mean, I don't know if you saw this in the quartic chapter. It's actually just not so easy. Yeah, it's just not easy. And so, right. Yeah. Anyway, so we'll get to some examples for this later on. All right. So yeah. So right. So those were both excellent questions, and I think the answer to both is that I don't know off the top of my head, and I think like it's your questions are at least close to things that nobody knows. So well, exciting, right? You know, it's exciting to get to something where you have a kind of reasonable question that no one on Earth knows the answer to. So, okay, we good to go on? Morning, Trent. There we go. All right, so let's keep going. So where were we? I think we're about to tackle the cubic. I think we did one example of a cubic. Yeah, we did one example. I think last time we talked about one example, just maybe a bit of a rush, but not in a terrible way. We tackled one example of a cubic. So let me actually remind you, perhaps it's actually appropriate to mention this here. So I think last time we figured out the Galois group of x cubed minus 2. So today we'll look at the general case of cubics. We'll look at one way of we'll sort of look at one method of determining the Galois group of any irreducible cubic polynomial. Excuse me. And this is not so bad. I mean, this is actually, I mean, just because there are very few suspects, this is not so bad. Quartic, as we'll see, that it's not so easy. It's not so straightforward. I think, as you can see in Artin, there's a little table that gets you down to sort of, there's just sort of one ambiguous case that's difficult, and then well, beyond that, there's just too many suspects. So again, it's just difficult. All right. So let me go. Let's go to the suspect list. So so the first step in computing the Galois group of an irreducible polynomial to degree n is you start off by listing all the transitive subgroups of Sn, and that, I mean, so for as even when n gets to I guess n equals 5 is not too terrible. N equals 6, things start to get hairy, and then, you know, if you go beyond that, it's in some ways unmanageable. So, you know, right. So you want to do that, but still, you know, for small n, this is still useful because, like as we said, we even with n equals 5, we get a remarkable result. So let's just first list some transitive subgroups of Sn. So those always include the full symmetric groups. So naturally, full symmetric, remember, transitive means that given any one point, it can in 1 through n, it can be moved to any other point, or equivalently by the FedEx argument, it's enough to show that you can move the object 1 to any other point. So these include the full symmetric group, because certainly the full symmetric group can move any point to any other point. Also true of the alternating group. I guess for n, I guess I suppose I should say that the alternating group only works for n greater than or equal to 3. But okay, you know, we always kind of know what the Galois group is for n equals 2. You know, it's the plus or minus in it has order 2 because, and it's the plus or minus in the quadratic equation. That's the Galois group. There's also the dihedral group is transitive because, I guess I shouldn't. So these are the full, and then we have a cyclic group, Cn, which sends 1 to 2 all cycles around to n, and I will mention that these are the full and rotational symmetries of an n-gon. Something that will actually come into play here later on. So there, oops. So there's so remember Dn is the full symmetry group of the n-gon, and Cn is the rotational symmetry group of the n-gon. Because we'll later see a square. I guess I should say the regular n-gon. Okay. But sort of, yeah, oh yeah, so when I was mentioning earlier that at some point this becomes hopeless, well, it is also true that any group of order n acts transitively on its elements. So you may remember that. That's like Cayley's theorem. So any group is a set of symmetries of its Cayley graph, and so any subgroup is isomorphic to a transitive subgroup of some Sn. So as you can imagine, as n gets big enough, trying to have a list of suspects and eliminating suspects is totally hopeless. But it does work for n equals 3, 4, and 5, the sort of thing you see in a course. Okay. Oh yes, and then in particular, when n equals 3, there are only 2 suspects because the alternating group A3 is isomorphic to the cyclic group of order 3, and S3 is equal to D3. The triangle group is I can't resist drawing a triangle here. The triangle group is, remember this thing, actually induces every permutation of 1, 2, and 3. And so there are really only 2 suspects. There's the symmetric group and the alternating group. Okay, so is everybody good to move on from the list of transitive subgroups of Sn, or some transitive subgroups of Sn, and all transitive subgroups of S3? So good. Okay, and so yeah, so we will, and we'll see when we get to 4. One thing that makes 4 a more difficult case is that there are a lot more suspects. All right, so here's some generalities about cubics. As usual, yeah. So now we actually are going to get to apply all the stuff about symmetric polynomials that we learned. So suppose f of x is written out this way when you multiply it out. So all these, so these elements, oops, these elements are in the ground field, capital F, and these, well, I guess K is equal to F adjoin the other ones, alpha 1, alpha 2, alpha 3. So suppose F is, a little f is irreducible over big F, and K is the splitting field of little f. And so, for example, and so we have the following tower of fields. F is contained in F of alpha 1, which is contained in F and alpha 2, alpha 1, alpha 2, which is equal to K, which remember we just said was F of alpha 1, alpha 2, F adjoin alpha 1, alpha 2, alpha 3. And that's true. The last one holds because, for example, alpha 1, alpha 2, alpha 3 is alpha 1 plus alpha 2 plus alpha 3 is equal to A1. And so if it is an element of F, of big F, and so if 2 of these things are in your field, then the third one is because you can just subtract them from A1. Okay, well, we know that because we're assuming little f is irreducible, the degree of alpha 1 over f is 3, and so we have this field degree, and we know that the degree of the extension k over f divides 6 of the order of S3. So either there's only sort of two cases. Yeah. So this is degree 3, and so what happens is that this degree over here is going to be 1 or 2. Those are sort of the only possibilities. And so either k is just equal to either this degree over here is, just let me get a better pointer here. Either this degree over here is 1 and k is equal to f adjoint alpha 1, and which means that the order that g must be equal to a3, or this degree is 2, and which means that the total the degree of k over f is 6, and g must be equal to s3. So these are so like I said, when you do the Galois group, it's at least when you have to do this by hand, you're not going to want to get in there and sort of look at individual permutations. You want to narrow down your suspect list and figure out sort of things that happen in general in your suspect list. So so that makes sense that we have 2 suspects. So Ravi, does that make kind of a little bit answer your earlier question? You're saying, like, how do you figure out, like, if a particular permutation is in your Galois group? And I think probably the answer that seems to work most effectively, certainly if you're doing things by hand, is that the most effective answer is that you don't. You try not to as much as you can. You try to figure out things in terms of invariance, and then sort of go backwards. Like, once you figure out what the group big G is, then you can actually prove that a certain permutation must actually be an automorphism. So yeah, okay. Right, at least it's I guess. Yeah, I will have to think about whether you can do that, whether it's reasonable to do that by hand. Oh yeah, it's probably okay. It's probably not, but by brute force. But it's certainly not easy. Okay, so any other questions about the getting down to 2 suspects for cubics? Okay. So so here, so this particular technique actually works in general, but it actually completely suffices to wipe out the cubic. So let delta be the square root of the discriminant. So remember, the discriminant is sort of this, except with squares. Well, let me remind you. The discriminant D is this, but everything's squared. Right, so do you remember the definition? The definition of discriminant, in order to be a symmetric polynomial, you had to square everything, because say if you switch alpha 1 and alpha 2, then this picks up a minus sign, and everything else is preserved, and so this is actually not a symmetric polynomial, but it's almost the thing that makes this interesting is it's almost a symmetric polynomial. So for example, delta is certainly is in K, because K is f adjoin alpha 1 alpha all these roots. It's not 0. It's non-zero because the roots are distinct, because we're assuming everything is in characteristic 0. And as I was just saying up here, since the discriminant is delta squared, and delta is going to be this plus or minus the square root of D, and which may be actually an element of f, and that's actually the thing that's going to determine what happens with the Galois group of a cubic. And so the action of any particular sigma on in S3 multiplies delta by the sign of sigma. I guess I should prove this. So if sigma is equal to, say, remember, so these things are called transpositions, and we already have an end. So I want to prove this in general. So in general, here's what happens. If you do something that, like, if you take the square root of the determinant in general, what happens if you why is this true, that the action of a particular permutation multiplies that the square root of the discriminant by the sign of sigma? Well, in one particular case, if sigma is equal to, I guess I should write this out by using pen, then sigma negates alpha I minus alpha I plus 1, and just permutes the rest. The other terms. Yeah, so yeah, you can sort of see. So for example, if you look at what the permutation 1, 2 does, it negates this, and then switches, and just sort of switches the order but since multiplication is commutative, that doesn't matter. So yeah, the permutation 1, 2 will just switch these other things, and the only one that really gets negated is exactly that term. And so and then as a fact, that every permutation is a product of transpositions of adjacent. Well, let's see, other form, switching I and I plus 1. And so you know, and the number of negations that you get will be equal to the number of those transpositions, which you may faintly remember from distant times, you know, like before coronavirus, which is like forever, right? Yeah, sort of. You may remember from last semester, the sign of a permutation is the number of every permutation is a product of transpositions, and its sign is even if, or plus 1 if it's a product of even number of transpositions, and it's odd, or minus 1 if it's a product of an odd number of transpositions. So and that's true. That's still true even if you just use these particular transpositions. Okay, right. So an odd permutation will negate delta, and an even permutation will preserve delta. Hey, that's like a good slogan. Let me write that down over here. Odd permutations, excuse me. Odd permutations negate delta. Even permutations preserve delta. In other words, leave delta invariant. Okay, so is everybody good with the square root of the discriminant? Okay. All right, so here is the Galois group of a cubic, and it just comes down to this. So so let K be the splitting field of an irreducible cubic little f over big F, and let big D be the discriminant. And let me remind you that we can. This is something you can compute. You can just you know, once you put your cubic in standard form, then it's just a straight computation by this mysterious little formula, which remember you can be obtained using symmetric polynomials. So again, let K be the splitting field of an irreducible cubic little f over big F, and let big D be the discriminant of F, I guess I should say. Discriminant of F. and let G be the Galois group, corresponding Galois group. And the theorem just says if D is a straight computation, look, it's like a little gadget you could compute, and then you'll know the answer. So if D is if capital D, the discriminant, is a square in the field capital F, then G is the alternating group on 3 elements. Otherwise, G is the full symmetric group. So and proof. So delta is in F exactly if and only if every permutation of G fixes delta. So so that which means, so yeah, that's so delta D is a square. So particular capital D is a square in F, that is delta is in F, if and only if every permutation of G is even. And let me sort of, I should draw some arrows to illustrate the logic here. So delta D is a square in F, if and only if delta is an element of F, if and only if every permutation of G fixes delta. And that's true if and only if every permutation of G is even, because we just saw that odd permutations negate delta and even permutations fix delta. All right, so and that's well, and that and when is every permutation in G even? Well, there's only 2 cases, and in the one case S3 there's some odd permutations, and in the other case A3 they're not. And so this is, I guess I should put this down here. This is true exactly when G equals A3. All right, so not not exactly a fireworks kind of proof, but there we go. Yay, we'll take it. So questions? Good so far? You know, I'm trying to, for the purposes of videos like this, or video lectures like this, I'm trying to figure out what's like a good positive indication. And I'm always struck that like every possible hand gesture I can imagine is obscene somewhere in the world. Like this is the middle finger in the Middle East, I believe. Anyway, have I told that story before? Okay, all right. Let me not preserve that story for you, but on YouTube. But so I take it everybody's good. So so now we completely conquered the cubic. Yay! All right. So let's see. Right. So now we move on to quartics. So right. So for the quartics, we're going to list. We start off again by listing all the suspects, the transitive subgroups of S4. So there's the full symmetric. Again, there's the 4 cases that always happen: the symmetric group, the alternating group, the dihedral group, and the cyclic group of order 4. And now we have a fifth example, because there is another. I mean, this is sort of this. This is the Cayley representation of the cyclic group of order 4 on its elements. And so now, but this is a new one. This is sort of again a representation of a group as a permutation of its elements, of the Klein 4 group. And so our question now is: given an irreducible quartic, which of these groups is its Galois group? And the answer is we can almost completely resolve this by, and actually now that you asked this, let me sort of, I'm going to make a note to look this up later, by hand computation. And I faintly remember actually like using some program that actually says compute the Galois group of this polynomial, and I think there's a way to do this. You know, I can't resist. I'm going to Google this. Okay, I don't have anything too embarrassing. You know, lecture tip: always make sure you know what's in your tabs in your browser. So how to compute Galois group by brute course. There we go. Well, okay. Let's see what this says. Oh my goodness. It's not so easy, I guess. All right. I don't know. All right. So well, at least I have the tab open, which remind me to look at this later. So maybe it's not so easy. Anyway, so as we'll see momentarily, after you look at, I think probably on Wednesday, by Wednesday we'll see that you can actually resolve. You can almost resolve this by hand computation, but not quite. There's like one ambiguous case. All right. So, but at least there's at least is everybody good with the five? Everybody's clear on the five suspects: symmetric, alternating, dihedral, cyclic, and our newcomer, the client for group. So okay. All right. So and now we're actually going to we will actually look at this case, which, as I hope you saw in the reading, the special case of this quartic here. And this is a special case where you can actually resolve everything by computation, by even a sort of set computation, which in your home, which you will figure out what that computation is exactly in your homework. You'll sort of figure out the right theorem and prove it. But so if you have a quartic where there are no odd terms, no odd degree terms, x to the fourth plus b x squared plus c, and we assume that this is irreducible. So the roots of that thing are going to look kind of like this. They're going to be after you use the quadratic form, they kind of look like alpha equals. Well, you start off with the square root of r plus root t, and then you take all the oops, oh no, I messed this up. So much for cut and paste. Well, this is why we do this. I can write these things live because, yeah. So, all right, sorry. Alpha minus alpha and alpha prime minus alpha prime. So you start off with alpha equals the square root of r plus the square root of parens r plus root t, and then you try all the sign SIGN variations on that. And so the idea is that if you have something of this form, x to the fourth plus bx squared plus c, this is sort of the same as saying that the roots of your polynomial, of your irreducible polynomial, are going to be this: alpha minus alpha, alpha prime minus alpha prime. And so, and this is getting back again a little bit to both Ravi and Mengru's question. So one observation we can make is that if you have an element phi of your Galois group, then phi of minus alpha is equal to the negative of phi of alpha. And so I like to think of this as a square. Ta-da, there's a square. What happens is if you have alpha over here and you have minus alpha over here, whatever is going, and say if you put an alpha prime over here and then minus alpha prime over here, whatever happens in the Galois group must preserve that opposition, and which is the same thing as saying that you preserve I guess the dotted lines did not help. Let me draw on the diagonals a different color. Right, so yeah, so whatever the action of G must preserve these green diagonals. Action of G preserves the green quote diagonals. I mean, which is just something we sort of made up here, but yeah. So G must be the elements. Each element of G is a symmetry of this square. I mean, I guess maybe it's not really. The word square doesn't deserve the scare quotes because it's something we made up. It's all something we made up, really. So right. So the point is that because the permutations in G have to preserve this opposition of alpha and alpha prime and minus alpha prime. Well, they're going to be symmetries as a square. So, oh, right, and which means that the point of that is that G is a subgroup of S4. Oh, sorry, of D4. And it turns out that both this initial restriction that we sort of know that G is acts transitively on the four corners of the square and as a sub and preserves the square. That cuts it down to three suspects. What is this here? Oh my goodness. Right. So I wanted to have some, let's see. So I wanted to have some notation here. So let's see. So we have sigma equals alpha goes to alpha prime and minus alpha prime, goes to minus alpha, goes to minus alpha prime. So that's the rotation. So sigma is this clockwise rotation as I've drawn it. I should do it. Sorry, I should only do that 90 degrees. There's sigma. And now I'm going to cheat, and I'm going to look up which tau matches what's in the book. Okay. Look, I'm caught on tape. All right, and so and tau is the permutation in Artin's notation that switches just alpha prime and and minus alpha prime. Okay, so well, that tau looks terrible. All right, so there, that's a better tau. Okay, and so so D4 is generated by sigma and tau, among other permutations. And so what is this? Yeah, so this makes no sense. Oh, I drew this wrong. Okay, sorry. No, this does make sense. I just drew it terribly. Right. So there are. So G is transitive, and so G is either equal to the full dihedral group on 4 elements, or the cyclic group on 4 elements, or D2. And it happens if you just list all the elements of those things that it contains both of these contain the following permutations. Alpha goes to minus alpha and alpha prime. I just made them look like polynomials because I forgot to put the space in. My bad. Okay, so I feel like I bet that this permutation notation. Now I see why the number Artin numbered them 1, 2, 3, 4. But okay, let me sort of write this out as. Let me write this out a little more clearly here. Okay, so let me just write the same elements with better handwriting of D4, of that particular D4, in better handwriting. Okay, so let me try that again. So we have sigma is a permutation that sends alpha to alpha prime to minus alpha prime. And tau is the element that flips alpha prime and minus alpha prime. So I hope that's a little better, right? Alpha goes to alpha prime goes to, so it's that cycle. And tau is that transposition. All right, so now that I've written that out with better spacing, does that, those elements sigma and tau make sense? Okay. Okay, and so the remarkable thing is that, so, well, not remarkable thing, the sort of the thing that makes this problem, that makes this particular subcase of quartics tractable is that, or one thing is that sigma squared, which is alpha goes to minus alpha, and the two cycle alpha prime goes to minus alpha prime. So so that sigma squared must be in G no matter what the case is. Yeah, so it's certainly not obvious, but so I guess Ravi, this is perhaps a pretty good example of how you deduce that a particular permutation is in is in a Galois group. So note that we deduce this. So, well, let me put it this way. So we use field theory, or properties of fields, to show that G preserves that square. I think that's sort of yeah, again, sort of getting to the question of both Ravi and Monroe. So we use properties of fields to show that G preserves a square, and groups to show that G must contain sigma squared. So, I guess this is maybe in some ways as good an answer as anything. You use whatever you can, and it's always going to be, and it will often be I guess it sort of has to be a mix of properties of fields, and also properties of, and so here we use this particular property of automorphism in order to show that the square is preserved, that G must be a subgroup of the group of the square, and then just by listing all the suspects, listing all possible transitive subgroups of the symmetries of the square, and just by listing them all, we say that we just observe that sigma squared is in all of them, and so we know that this particular element is in G. So right. Any questions so far? Yeah. Oh, questions in the chat. So Ravi asked, do we say that sigma is in G? Sometimes sigma will be in G. So that's an excellent question. Question, is sigma always in G? And the answer is not always. Yes, if G is equal to D4 or C4, yes, but otherwise, but not if G equals D2. So we don't know. So I mean, this is exactly the point that your excellent question and Monroe's excellent question, and we're getting at. We start off by knowing, like, okay, we have this particular permutation of the roots of this equation of this roots of this irreducible, but we don't know. It's hard to figure out at least at first, whether this particular permutation is actually in the Galois group or not, whether it actually leads to a field automorphism. So it's hard. Oh, so it seems like it's never in G because it doesn't preserve the green lines. it can be the case that G is in, sigma is in G because it preserves the green lines setwise. If just not individually. Ah, now we are speaking my native tongue here. There we go. Right. So right. So I was maybe a little again. Here you go. You actually caught me talking my native idiom of my native tongue here. So so when I say that the action of G preserves the green diagonals, it preserves them as a set. So it could sort of switch the two green diagonals. And so when you rotate by sigma, it sends the prime diagonal to the unprimed diagonal and the unprimed diagonal to the prime diagonal. So it preserves. So sigma preserves the green lines as a set, and that's all this kind of guarantees you up here. It tells you that negatives are each pair of negatives is sent to some pair of negatives, but it could be the other pair of negatives. But it is yeah. So Robbie, does that make sense? As sort of why it's possible that sigma is in G, even though it's not necessarily in G for different cases. Yeah, it's tricky. Right, and so but the strange little thing that we get here is that sigma squared is always in G, no matter what. And so and I guess actually let me pull back and explain why that's significant that sigma is always in G. The reason this is it's interesting that sigma squared is always in G. So what we're going to do is we look at field elements invariant fixed by sigma squared. I mean, I guess you don't really need to know that. Oops. Oh no. What is that doing up there? Okay, hang on. All right, I guess you don't actually need to know this. Let me start type again. So we look for field elements invariant under sigma squared. So because we're actually going to look at the fixed field of the group generated by sigma squared. Okay, so there's oh gosh, there's this terrible typography again. It looks like alpha minus alpha. So this is so let me pull back. So again, let's pull back, pull out, push in. Sorry. And so what we have here is that we have what we have is no, that's what I want. The pen. Hello, pen. All right. So again, this is so let n be the subgroup generated by the permutation that switches alpha and minus alpha, and at the same time switches minus alpha prime and minus alpha prime. And so we see that since this permutation just sends alpha to minus alpha, that fixes alpha squared, and since the permutation at the same time sends alpha prime to minus alpha prime and vice versa, and we'll preserve each of alpha squared and alpha prime, alpha prime. And each of those is a square root of some. If you square those, then you get some. Oops. Each of which is not the square root of an element of f. Is actually, let me put it this way. Each of which is contained in a field. No, don't do this either. Yeah. Whoa. How do we erase this thing? Is it gonna work? Oh yeah, that did work. Okay, there we go. Each of which is, all right, let me fix that. Each of which is contained in some f adjoined square root of s. Right, because if you look, so for example, if you look at, I should actually say what alpha squared and alpha prime are. So alpha squared, remember, if you go back and look at what we had over here, is going to be equal to r plus root t, which is contained in f adjoin root t. And then alpha prime, well, if you multiply out what we had before, if you multiply that r inside the square root r plus root t times r minus square root t, then you get the square root of r squared minus the square root of r squared minus t. And that's certainly contained in f adjoint a square root. And furthermore, if we let's let L be f adjoin alpha squared and alpha prime, and so we have the following tower of fields. So n fixes alpha squared and alpha prime, and so n fixes L. So L is contained in the fixed field of n, and so we have so there we go. We have this tower of fields, and we know that this degree here is 2 because of the fixed field theorem. And and so the question is, sort of which of these things, if we look over here, which of these degrees are 2 and 4, and that some just a little bit of extra work coming from field elements will tell us what the Galois group of G is. So the two questions are to sort of resolve here, what is the degree of L over F, and which elements send alpha to alpha prime, for example. And remember that G acts, and this is actually sort of getting to what both Ravi and Monroe are asking about. If so G acts transitively on the roots, so 1 exists. Must exist. And so this is sort of this is kind of a combined answer to both what Ravi is asking and what Monroe is asking. So once we get down to this level of detail, we know that since G acts transitively on the roots, that there's going to be some element sending alpha to alpha prime. And so so there's going to be something sending alpha to alpha prime, and then sort of using these other known properties, we figure out what where alpha, like minus alpha, goes, and so on. All right, so okay, so so sort of resolving these two questions, as you'll see in the homework, and you'll sort of figure out the theorem or the sort of handles this in general. Resolving these questions, like what is the degree of L over F, and which if you have a Galois group element that sends alpha to alpha prime, then you can sort of deduce what the other elements, which elements I should say of G. Send alpha to alpha prime. So for the full solution, that's worked out in the problems. That's actually, I think it's 16.9.5 is the sort of working out more or less a formula, a full theorem for when you get the dihedral group, when you get C4, and when you get D2. And so we're going to just do one case. All right, so so in this particular case, let alpha be the fourth root of 2. And this is so this is going to be equal to x minus alpha times x plus alpha. That is x minus, well, say x minus alpha, x minus I alpha, and x minus I alpha. So those are the four roots of that equation, and so that's how that factors. So let L be f adjoin alpha squared, and alpha squared is square root of 2, and alpha prime is going to be equal to well, alpha times I alpha. So this is I times the square root of 2. What is the degree of L over F? Well, the degree of oops. So that's equal to the degree of L over F of alpha squared times the degree of F of alpha squared over F, right? This is, so F of alpha squared is equal to F adjoin root 2. So this is 2. So this degree over here is 2. And let's see. So and we also know that that L is not equal to. So for example, this is also going to be equal to 2 because this degree over here is also going to be equal to 2 because because F of alpha squared is real and L is not real. And so we see that the degree of L over F has to be equal to 4. Yeah, and yeah, we sort of I guess this shows, this calculation over here shows that L, the degree of L over F of alpha squared is at least 2, because it's not, because L is not equal to F of alpha squared, and the degree of this element is at most 2, and so it has to be equal to 2. All right, and so L adjoin L as an extension of F has degree 4. So so we see now that that we have the Tower fields F is contained in L, is contained in K. The fixed field of K is contained in K itself, and we know that this degree here is 2, and this degree here is 4, and we know that this that the degree of K over F has to divide 8, and so it must be equal to 8. And so we deduce that this degree in the middle has to be 1. There's only one suspect, and so L is equal to the fixed field of K. And so we also deduce that the order of G is 8. And by process of elimination, there's only one degree of order 8 in our list of possibilities, and so G must be equal to D4. All right, and yeah, so we see. I guess this is, so I guess we'll do this case in more detail. Start looking at this case in more detail on Wednesday. But let me sort of see that here's where you sort of see a combination. The interesting mix of techniques that you use in Galois theory. Over here, we're using sort of field theory. We're using field theory to compute the order of G, and then here we're using group theory to take the order of G and then reduce the number and sort of using our limited list of suspects, figure out what G actually is. So I guess you know, that yes, this is the example. This is a good example of sort of of uh, the answer to sort of both Ravi's and Mengru's questions. You use this lovely combination of group theory and field theory, sort of working together, and you know, and using things in one language. It's in group theory that you couldn't possibly, that'd be much more difficult to deduce than the other, and then using things in field theory that would be much more difficult to deduce in group theory. And I don't know, it's all one, as the Buddha said about the hot dog, make me one with everything. It's all one, man. All right, so I'm like way over time. I should stop now. Thanks very much for your patience. See ya. Bye.